Welcome back, everybody. So we're going to, I'm looking at our calendar and I decided that I'd rather just, because I know the next section as well is also going to be one that is a little intense. Um, I'm going to delay doing 0.8 until next week. That way you're not rushing, scram like because I'll have it ready for you guys. I'm putting on some finalizing touches, but I'll have it ready by this weekend, so you'll have all weekend to print it off and get it ready. So plus, I think there's a lot of material that we've been going over, and I think it might behoove us to do a little bit more practice on certain things here. And then additionally, what's it called? Rational zeros theorem can be a little intense at first, so we'll talk about it bigger time with it. So yes.
It's 0.8 in this unit too.
So yes and no, because so in 0.8 is all about rational expressions and how to work with them and how to solve equations with stuff. But and so we need that in order to talk about rational functions. So it is on the exam, but it's not really going to be tested on the exam because it's just preliminary information. I might change my mind and I might incorporate some stuff in there. And that is that there is a reason to that too as well. In calculus, you will have to do certain things with rational functions a lot. So it's good to get plenty of practice with them. So I might even just incorporate that into the exam. Um, but the good news is, I mean, it's all stuff that we're going to have to know how to do anyways. So, okay. Any other questions? Sure.
Days ago, I was doing it, had a graph similar to this, and it said like create an equation, or it's like how many, what is the option of the behavior? It was like 2, 4, 6, 8, and then there's 5, 7, 9, and I put like 2, 4, 6, and 8 because it was an even function. But it said it has to be more than like the certain number of maximum minimums.
Okay. So let me look at that during the break and get one of those problems pulled up. I
You
think
know what I'm talking about?
I believe I know what you're talking about. So it might be that it didn't like the using of two because like was it asking about the overall degree of the polynomial or the degree of a zero?
The overall, and because it had like 3 humps, it couldn't be 2, it had to be at least 4, something like that.
Yes. So that there's a thing that there's like there are three random rules in this section. One of them is called Rene Descartes' rule of sign. There's another one that's called like the min-max theorem or something like that, and that's the one that's being referred to there. That says that you like your degree of your function has to be more than the number of humps that are in it, the peaks and valleys. But it's such a niche situation that I don't teach it because it's not useful. Like the only situation where I've ever seen that ever used, ever, was on the math GRE, which is like the big boy SAT for subjects. So like you know how there's a subject is there a subject SAT anymore? Like a specific math? I don't think so. But in grad school, in order to get into grad school, there's the GRE, which is basically the big boy SAT, and then you also have to take your subject GRE. So it's going to be like for mine, it was a math GRE. For my friend who was in English, his was an English GRE, and he had to read like 20 books and have them memorized for that exam or whatever. So mine was going to be 50% calculus material, 25% special topics, 25% linear algebra. But point being is I only saw that question ever on that exam, and I've never seen it ever since. So it is a niche topic that does have uses, but like unless you're planning to go into mathematics, you're never going to use it. And even then, it's only useful right now. In calculus, it'll go all the way, and you'll never need to know that. So it's a stupid thing. I'm guessing that it had to do with the fact that you used degree two, and I'll explain why in just a moment. So
I just didn't, I've never seen it, and I was like, oh, did I fall asleep or something?
no,
If we don't use it, then that's fine.
yeah,
I figured it out.
I will not be testing on that. So do not worry about Rene Descartes' rule of sign. It's a nifty trick. It was Rene's or Descartes' rule of sign was great back in the 1500s when we didn't have calculators and we weren't able to do mental math as quickly. But now we've learned so many different techniques to do mental math quickly. He didn't have synthetic division. back in the day. He didn't have that. So like synthetic division is relatively new. So he, in order to check whether or not something was a factor, he had to sit there and do long division over and over and over again, and that was not fun. So he created his own little rule, and it was awesome back then. Totally moot point now. So okay, so on to this one. The graph of a polynomial g is given below. Find the possible things. We talked about it. So we're looking at it. We know its end behavior, and look, based on its end behavior, what degree is it? Is it even or odd degree? It must be even because both are pointing the same direction. Even degree polynomials, they either point both up or both down. Odd polynomials either do that one like they do the cactar, right? If anybody knows their Final Fantasy. Cool. Does anybody else know Final Fantasy? Cactar? What?
Kingdom Hearts.
Kingdom Hearts, yes. So the cactar is in that, right? That guy. Really, really cool. If you haven't, they did a Final Fantasy set in Magic the Gathering and they broke the game with cactar. They really did. If you're a Magic person, that'll make sense to you. But if not, that's absolute gibberish. Way too expensive, and they've really started to do too many sets. But that's not important. What is important is this. So we were looking at this, and we were looking at all of the zeros. We've identified them: -1, 2, and 4. And then based on their behavior at those zeros, we can determine whether or not it's even or odd. And I said find possible equations because there are infinitely many that could work. So we saw that this had to be, let me use this. This had to be even because it bounces. This had to be odd because it crosses through. And this also had to be odd because it crossed through. Then I recognize that there's more wiggle, there's more jaggedness at 2 than there is at 4. So this probably has a higher multiplicity. On the exam, though, if this was showing up and you used multiplicity 1, you'd still get full credit. Because all I really want you to recognize is the pattern of multiplicity, like the behaviors of multiplicity. The making sure that it actually has the wiggle, that's less important. But either way, this means that we know that f of x, so all of this implies that f of x will equal a times x minus -1, so x plus 1. And we're going to assume squared, but if you really wanted to troll me on the exam, you could do this. You can make it x plus 1 to the 20,000. You could. I don't recommend it, and I'll explain why in a second, but 2 is a good enough choice. And then x minus 2, and I'm going to say raised to the 3rd power, but you could do the 31st power or the 301th power, whatever you want to do. And then last but not least, x minus 4 raised to the 1st power. So this one, it wasn't implied. I think I'm going to edit my notes. So 2.3.8. I'm going to actually do this one second. Didn't I make one for 126? Did I do that? That's my calc note. Okay, I'll add a new one here. 2.3.8, add solid dot. Okay. So it should have a solid dot there. And on an exam, if I have this, I will make sure that it's very clear that there is a point on the curve that you can use. If there is no given point, and it's not very clear where there's any graphing grid lines where it crosses the x, has a point that's a nice point to use, then we can just make sure that we use we can just make a equal to 1. But we know f of 0 equals -4. So that tells us that a times 0 plus 1 squared times 0 minus 2 cubed times 0 minus 4 is equal to -4. And then we just have to go. So this is the reason why I don't recommend making the powers too large, because imagine it won't help, it won't hurt too much here with with this one because it'll just be one. The 0 plus 1, that'll be 1. And so 1 to the 20,000th isn't a big deal. But -2 to the 31st is a very, very, very large number. So you'll start getting some really, really nasty things. So keep it small if possible. So 1 squared is 1, -2 cubed, that's -8 times -4. That should be positive 32. So we get 32a is equal to -4. And so that a is equal to -1/8. And so we have our final answer that f of x is equal to -1/8. And that lines up. This should have a negative leading coefficient because both are pointing downwards. If we got a positive coefficient, that wouldn't make any sense because that would mean that both sides were going up because this is an even degree polynomial. And we need we need the end behavior to be both falling on the left and falling on the right. So it should be negative, and we got a negative, so we're happy with that. So x plus 1 to the second power times x minus 2 to the third power times x minus 4 to the first power. And that is one possible answer. Without enough information, we don't know if it's the third or the fifth or the seventh power, but convention would be to choose the smallest one that you can. Any questions on that? Correct. Cool. Uh-huh. Sure, sure. So I know that f of 0 is equal to -4 because I was given that point on the graph. And so if I plug in 0 for x and replace f of 0 with -4, then all that's left is just a to solve for. So everything else goes away, and there's only one variable to work with. Good. All right. Now, I'd like to do the challenge problem because I think it's a really, really good problem at understanding the implications of the factoring theorem. And this one really gets us to think outside the box. So we're going to feel uncomfortable for a second, of course, because it's looking like a strange problem. There's a reason why I called it a challenge problem, because at its core, it looks strange. But am I able to copy this? Am I able to copy and make a new page? Will it let me paste? Yay, it does. Okay. So I have the like you can see the answers upside down. It says, suppose that f of x is the function kx squared minus 16x plus k squared, where k is some constant. Find the values of k for which x minus 2 is a factor of f. Okay, that's intimidating, not gonna lie. As you go further and further into mathematics, you start to become very, very comfortable with the fact that some things are numbers, but not numbers yet. So this has two different variables. It has x and it has k. But the thing to remember is that k is a fixed number. We don't know what it is yet, but it is a fixed number. X varies with whatever we want it to be. X could be 5, x could be 2 billion, x could be -7. K, we don't know what it is yet, but it's just some constant. So we have to be able to find k somehow, some way. And it says, find the values for which x minus 2 is a factor of f. And my recommendation all the time with you guys, and I hope it's sticking at this point, is if you don't know where to go, say what you do know. So x minus 2, zoom back in. What could we say if we know that x minus 2 is a factor of f? There are many things we could say. So we have our big boy factoring theorem. There were three main results that were important, and there were two other ones. But if we know that it's a factor, that means that we know. Oh, I didn't mean to put a question mark there. I meant to put a double arrow. That means that x equals 2 is a root. slash 0, right? If it's a factor, then the x equals 2 is a root. And what does that mean by definition? If it's a 0 or a root, the other name, it means that when you plug it into the function, you get 0. So this means that f of 2 is equal to 0. And that is important because that allows me to create an equation. Because keep in mind, f of x is kx squared minus 16x plus k squared. That is a function that has k's and x's in it. I can now replace the x's with 2's, and I can set that equal to 0. So that is to say, f of 2, by definition, that would be k times 2 squared minus 16 times 2 plus k squared. And so that is equal to 0. And that's a polynomial equation, purely in terms of k now. So let's write that down and then let's re-understand it one more time, because that is definitely a strange situation when you first encounter it. I even had, like, my calculus students even sometimes have troubles with this type of a concept where you have an unknown constant and a variable x. So keep in mind that f of 2 means you're plugging in 2 for x, not for k. K is some unknown thing. It's some unknown constant. So because it's a factor, that means that x equals 2 is a 0. And because it's a 0, we know that f of 2 is equal to 0. So we can plug in 2 for x. We get this equation. Rewriting it a little bit better, so that's going to be 4k minus 32 plus k squared equals 0. I like to see my polynomial equations in descending order. So I'm just going to rearrange it. I'm going to rewrite it as k squared plus 4k minus 32 equals 0. And that is a polynomial, and we can factor that. We don't even really need to factor it. There's no real, like, we could use the quadratic formula if we're really strapped for time and we don't want to spend the time factoring it. But this thing does factor rather nicely. It factors to k plus 8 times k minus 4. And you can use whatever methods you want to factor that. So you don't even really need to use bottoms up race. You just need to find two numbers that multiply to negative 32, and the same two numbers have to add to 4, which would be positive 8 and negative 4. That gives us that k is equal to negative 8 and positive 4. Any questions on that? It's a really cool problem, in my opinion. I think this is a very, very clever problem. Just this is if you're interested in mathematics at all, by the way, if this problem was satisfying, if you liked this problem, you might be interested in mathematics. This is the type of stuff that you really, really encounter in upper division, is this kind of concept of you don't know what something is, figure out why by deduction. Instead of like, here's the useful property, use it. It's thinking with these abstract problems. No real life application, right? This is not useful in any other situation other than in this class, but still. Okay. Let's see here. All right. And do you want to take a picture real quick, or you can wait until after class? Cool.
Is video recorded?
Yeah, it is recorded. So okay, that's fine too. All right. On to the rational zeros theorem and the fundamental theorem of algebra. Now, I wish that we had more time to talk about the fundamental theorem of algebra. I wish we could go into more of its details, but we don't really talk about complex numbers in this course. And so it's not super relevant to us anymore. The fundamental theorem of algebra was created, was discovered by Carl Gauss. I think I've mentioned his name before. If I haven't, no big deal. Gauss is probably one of the most famous mathematicians, specifically because of the fact that he was considered the last mathematician who knew everything about mathematics. So as we've grown as a society, we've added more and more and more to mathematics that we've learned over the years. So during his time, there was less known, but he knew everything. Nowadays it's impossible to know. There's just too much information, but he literally knew everything there was to know about math at that point. So that was pretty cool. And what he discovered was this thing called the fundamental theorem of algebra. You'll see this pop up time and time again in mathematics. There's almost always a fundamental theorem of blank. So in number theory, there's the fundamental theorem of arithmetic, which we've talked about, that says that every number can be broken up into a product of prime numbers. 6 can be written as 2 times 3. 8 can be written as 2 cubed, and so on and so forth. And that doesn't seem like a big deal at first, but that's a very, very central concept that helps us prove a lot of things in number theory. There's the fundamental theorem of calculus, which is very, very essential to our understanding of calculus. And this one is super important to polynomials. If f is a polynomial of degree n, then f has at least one zero or root. Now that seems like a clear statement, right? If it's a polynomial, it has to have at least one zero. But proving that is actually quite a challenging thing. But the more important implication as a consequence, the far more useful fact is that all polynomials can be factored into linear terms. That is to say, f of x for any polynomial can always be written as a times x minus c sub 1 times x minus c sub 2 times dot 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 times x minus c sub n. Where the c sub 1, like the c sub blanks, the c sub i's, if you is the way we usually say it in mathematics, the c sub i's for any I between 1 and n. So all those numbers, they could be repeats. But the fact of the matter is, that's the way it's worded, but the bigger implication is that every polynomial has some way, somehow, can be broken down into purely linear bits. And then the reason why we won't go too far into it is that the real big use of this is studying complex numbers and the fun little observations that come with that. If I had more time in this class, I would definitely spend time talking about complex zeros, because there's a very, very interesting fact here. So to show you an example of how the fundamental theorem of algebra gets applied, I have this degree 5 polynomial. And if you want to factor that, it becomes 2x plus 3 times x minus 2 plus I times x minus 2 minus I, and then x minus the square root of 5 times x plus the square root of 5. The point of writing this is to show you that the c sub 1, c sub 2s, they could be nice numbers. They could be like 1, 2, 3, or 4, but they could also be complex numbers. They could also be irrational numbers like square root 5. And so just a fun little observation just before we continue onwards. Do you notice that, so it's x minus 2 plus I and then x minus 2 minus I. And one of the cool things about this is if you have one complex zero, you automatically have its complex conjugate as a zero as well, which is really, really interesting. So like zeros, real zeros can come in singular digits. You can get 1 0 just show up once, it can show up twice, it can show up 3 times. And it could be that like if 2 shows up, it's not guaranteed that negative 2 shows up. But with complex numbers, if 2 plus I shows up, 2 minus I will also have to show up. If your polynomial has a 0 at 1 minus 2/3 I, you will also have a 0 at 1 plus 2/3 I, which is a nifty little consequence in mathematics, but not super useful for us. The reason why I bring this up, though, is that when we were tasked with factoring that m of x equals 3x to the fourth minus 11x cubed minus x squared plus 19x plus 6, we were given the fact that m of -1 and m of 3 equaled 0. But what if we weren't given that information? How would we be able to find it? How would we be able to factor it? The fundamental theorem of calculus tells us that there is some way to do it. And so there must be something that we can figure out. And so mathematicians were plagued with that for a very, very, very long time. And we've learned different methods over the years. There's a thing called Eisenstein's criterion, not Einstein, but Eisenstein, just another Greek, another German dude. Because of course it's a dude, because mathematics was very, very sexist at the time. Still is at some points, but either way, neither here nor there. We've learned several of them, but the one that is actually applicable at this stage in our mathematical understanding is called the rational zeros theorem. Very, very annoying theorem to prove, but it is a very, very useful one. It says, let f be a polynomial with integer coefficients. This only works if there are integer coefficients. So we're talking like -5, 3, 7, 200, whatever it may be, but no fractions, no irrational numbers. So f of x is going to be a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 0. Then the possible rational zeros are of the form x equals p sub 0 over q sub n plus or minus that. Which, what does p sub 0 and q sub n mean? These are plus or minus the factors of a sub n divided by the factors of q sub n. Of a sub. Oh my God, it should be factors of a sub 0 up top. I'm sorry. P sub 0 over q sub 0, where p sub 0 is a factor of a sub 0 and q sub n is a factor of a sub n. Looks really intimidating at its standpoint. Once you see it in action, it'll start to make way more sense. But there's a reason why, like, so most textbooks will write it as x is equal to, so don't write this down, but most textbooks will write x is equal to p over q plus or minus, where p is a factor of a sub 0 and q is a factor of a sub n. But I found that that didn't really make much sense. Like, why is p being used for a sub n? Why is p being used for a sub 0 and q being used for a sub n? So I decided to add my own little subscripts. So p sub 0 and q sub n to correspond to a sub 0 and a sub n. And so you're probably wondering, why is this here? Why is this super cute little toucan there? And why does he have a top hat? And why does he have a pencil? Well, we all know good old Toucan Sam, right? Toucan Sam, he follows his nose. And in mathematics, that's what you're supposed to do. You're supposed to follow your nose. So this isn't Toucan Sam. This is, so remember, this is Pooh Can Sam. I'm trying this out. This is my first time using this. I'm hoping it's going to stick. I'm hoping it's going to think about it. So you can just remember this Pooh Can Sam. I know technically it would be Po Quinn, but Pooh Can Sam is good enough for me. So P sub 0 over Q sub n. So maybe that'll help you memorize it, maybe not. Otherwise, fun fact, I did not draw that. AI drew that. AI created that image for me. To create toucans, you can, like, one thing you can tell the reason why it's AI, it's right there. His beak shouldn't continue on past the line of his beak shouldn't continue on past that. But isn't he so freaking cute? Maybe the cutest little guy ever. Anyways, okay. So how do we use it? How do we actually use it? I should actually add that here. I'm actually going to move this up and say how to use it. we can list out all possible choices of zeros. You could also put this underneath example 2.4.1 if you didn't have enough space. We don't need too much space for 2.4.1. But how do we use this to do anything? We can list out all the possible choices of zeros and then plug them in into our function to see if they're zeros. Then use synthetic to factor. Utilizing that good old Poocan Sam. Maybe I can make it P sub A sub 0. So it'd be pow can and Q sub A sub n. So it'd be pow can Sam. But Poocan Sam sounds sillier. So what the rational zero theorem tells us, the RZT is what we usually abbreviate it to. The RZT tells us that if we do have zeros that are real numbers, they're gonna be of that format. So what we're gonna see is we're gonna get a lot of answers. And we don't know which one works, but we know that if it does have a zero in that set, it's gonna be one of those numbers. So let's see it in action. So list the possible rational zeros of f of x equals negative 4x to the fourth plus 5x cubed minus 32x squared plus x plus 8. So with this one, we have no way of factoring this with our current information except for the rational zeros theorem. So the possible zeros are of the form x equals Poocan Sam, so plus or minus p sub 0 over q sub n. And so remember, these are the factors of a sub 0, which is equal to 8. The factors of 8 are 1, 2, and 4, and 8. Q sub n, that corresponds to a sub n. These are the factors of a sub n, which is negative 4. And so, technically speaking, we would write like the negative sign doesn't really matter to us. And I'll explain why, is that we already have this plus or minus sign here. So like even if I just wrote -1, -2, and -4, it would just get bypassed by this plus or minus. It would just take care of itself. So just look for the factors of 4. Don't worry about the negative sign in front of it because the plus or minus that's there is going to take care of that for us. Yes. How do I know to choose 8 and 4? So the P sub 0 is one of the factors of A sub 0, and A sub 0 is this. A sub 0 is always the constant term. It has degree 0. That's why it's A sub 0. And A sub n is your highest degree term. So that's A sub 0, and then let's highlight this one. That's a great question. Thank you for asking that. That is A sub n. And so, oh yes, JT.
Sorry, you said leading coefficient be a sub n?
Yes. Like if you look like so, thank you for bringing that up. Let's recap that real quick. We always write a generic polynomial as a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 0. So a sub n x to the n is always our largest degree term. It's always our first term. In my class, I will always make sure that the polynomials are in descending order. So a sub n will always be your first one. A sub 0 will always be your last one. It'll always be your constant term. So the factors of 4 are 1, 2, and 4. All right. So this will equal plus or minus. Now it's a matter of writing all the possible options. And so once you're finished writing, I'm gonna show you what I mean. There's in total in this situation, there are 12 total possibilities, plus or minus. So technically 24 possibilities. The way you list them is basically fix one of the things. Fix it to be like, start with the, like, I usually just start with fixing the denominators and then listing all the possible numerators. So what I mean to say is that this would be 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, and plus or minus 8 over 1. Those are all the different possible factors of a sub 0 over the factor 1 for the denominator. Then we'll move on to the next factor of a sub n, which was 2. It says 24. I don't know what. There's a missing comma there. And then plus or minus 1/2, plus or minus 2/2, plus or minus 4/2, plus or minus 8/2. And then the last factor of the denominator, like the last possible factor for the denominator is 4. So we also get plus or minus 1/4, plus or minus 2/4, plus or minus 4/4, and plus or minus 8/4. So let's talk about, like, once you've written those down, and I hate writing the plus or minus every single time. I typically just write plus or minus at the beginning and then just keep using commas. That's okay on the exam. I think Alex will want you to write a plus or minus each time, which is really annoying. And I'm sorry for that, but it just has to be done that way. That's the only way the program can understand it. But on an exam, if you just write a plus or minus at front and then write all the list all the possible zeros, that's fine with me. So let's once again recap that, because that's weird. That's weird. There are many ways you could start it. This is another way to do it, by the way, and hopefully this will make it make more sense. Maybe I should have color coded it. So this is another way you could have done it. You could have fixed the numerator factor and gone through all the denominator factors. So this would be another way to write it. You'd go, okay, I'm going to fix the numerator to be 1 at first. So it'd be x equals plus or minus. This time I'm not going to keep writing the plus or minuses. So just so you see what's going on. 1 over 1, comma, 1 over 2, comma, 1 over 4. And that's covered all the possible situations where the numerator is 1. Then we'll move on to 2 and go through all the different denominators, the 3 different denominators. 1, 2, and 4. So then I can do 2 over 1, 2 over 2, 2 over 4. And then I do it again with 1, 2, and 4. And this will be 4 over 4, or 4 over 1, 4 over 2, and 4 over 4. This is another way to do the same thing. Are we seeing how it's done? It's okay if we're not. Please ask if you're not seeing it. It's really important that we understand how to set it up, because otherwise we can't do the rational zeros theorem. So I'm just going through all the possibilities. I'm going through all the jumblings. Do we see the pattern? It's okay if we don't. All right. You'll notice, however, that there are some repeats. And I'm writing it in full detail right now, but I'd like you to do the mental math, the little bit of arithmetic, a little bit of division on the side, right? I don't need to write the dividing by ones, right? I don't need to do that. It's unnecessary. I already know that dividing by 1 does nothing. So I can just write plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. But then we'll notice a couple things. This one right here. Oh, I'm gonna use pink. That one, that's just 1. but we already have that right there. So that's redundant. 4/2, that's 2. We already have that. 8/2, that's 4. We already have that. 1/4 we don't have yet. 2/4, that's 1/2. We already have that. 4/4, that's 1. We already have that. And 8/4, that's 2. We already have that. So these are all redundant. These are redundancies. How do you spell redundancies? Just say already mentioned. Nobody knows that you can't spell, right? Cool. I just don't know how to spell redundancies, and I don't want to look it up. All right. So if we really wanted to, we would just write it as plus or minus. The possible zeros are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 1/2, plus or minus 1/4. And that should be it. Yeah, that's it. Any questions on that? So while you're working through this, and we're going to do this several times, so don't worry, you're going to get plenty of practice. But go ahead, and if you've already listed it, just don't write it. So when I'm doing this, and we'll see this in the next one. Okay, we'll do it there. So I actually discovered something. So I'm teaching this course, and I'm also teaching regular 126. And they just went over this last week, and I thought of or not last week, 2 weeks ago, and I thought of a really nifty trick. Because the way I used to teach it was you'd list all the possible zeros, and then you'd use synthetic division to see if it's a zero. But that takes a long time and a lot of space on a paper. We have calculators for a reason. So we'll get to that in just a moment. So with this next example, factor this polynomial completely. There is no way to factor this with our current understanding. So by the rational zeros theorem, so by RZT, which we're going to call RZT from now on, possible zeros are x equals Pucan Sam, so plus or minus p sub 0 over q sub n, where p sub 0 represents factors of a sub 0, and q sub n represents factors of a sub n. That's why I use the 0 in the n. So I'm going to highlight them and say, so which one is a sub 0? What number is a sub 0? 8. So factors of a sub 0 would be 1, 2, 4, and 8. And a sub n is our leading coefficient. So it's the 3. And the factors of 3 of a sub n are going to be 1 and 3, because 3 is a prime number. If it was 6, we'd write 1, 2, 3, and 6. If it was 12, we'd write 1, 2, 4, 1, 2, 3, 4, 6, and 12, so on and so forth. So I've always done it by fixing the denominator and writing them that way. So this would be plus or minus 1 over 1, which is 1, 2 over 1, 4 over 1, and 8 over 1. Then there's 1/3, 2/3, 4/3, and 8/3. Please ask a question if you don't see where that came from. Please, please, please. I've always found this to be the weird part. Once again, what the rational zeros theorem is saying is it's saying that if it does have a real zero, specifically one that we can work with, it's going to be of that form. It's going to be one of those numbers. And that's a total of 1, 2, 3, 4, 5, 6, 7, 8. That's a total of 16 options. Do you really want to go through and check 16 things? Probably not. So, pro tip. Start with the nicer numbers and pray. Because I really don't want to go through and plug it. Like, so sometimes with these ones, it gets to be obnoxiously long, the list. But usually speaking from a teacher's perspective, and then also speaking from the Alex perspective, they rarely make the big numbers or the really, really nasty fractions one of the zeros. Almost always, at least one of them is a nice integer number. So test the integers first, test the small integers first, then test the small fractions, and then if all else fails, then go to the big numbers. Unless, of course, you see really, really, really big numbers and from the get-go, like if that said 800, I might be inclined to test the big numbers. If it said 72x squared instead of just 7x squared, I might be inclined to test the big numbers, but few and far between. Okay? So the way I used to teach it was I would say, okay, well, we'll test one. We'll do synthetic division. We'll do 1 divided into 3x cubed minus 7x squared. Don't write this down. Minus 22x plus 8. And I'd go through, bring down 3, negative 4, negative 4, negative 26. Nope, this isn't going to work. But that takes a lot of space on the exam. That takes up a lot of space on your work. And it's a lot of work with little payoff. We have a calculator. So, key. Plug into F to see if you get F of blank equals 0. Because what would that mean? If F of 1 equals 0, what would that tell us? It would tell us that x minus 1 is a factor. If f of 1 equals 0, x minus 1 is a factor. If f of negative 5 equals 0, x plus 5, so x minus negative 5, x plus 5 is a factor. If f of 10 equals 0, then x minus 10 is a factor. And we can use synthetic division to factor it out and work through it. So in particular, so I'm going to write that down here. Because then we know x minus that number is a factor, and we can use synthetic division to start factoring. So people watching the recording, you're not going to be able to see this. So if you're watching the recording and you don't know how to do this on your calculator, come talk to me after class, before class, or during my office hours, and I'll show you how to do it on your calculator. This is why I highly recommend, don't forget your calculator on this next exam. If you bought a Texas Instrument, specifically one of the higher models, the 3i, the 32XIIS or whatever it is, not the curvy one, not this one, not this abomination, not that one. That one's a bad one. It's not bad, it's just not great. But if you have a Casio, then it'll be like, they always have a store property. You can always press back or press up to edit what you put in. So watching what I'm gonna switch over the document camera for just a moment. Oh wait, no, not yet, not yet. I'm gonna show you what I mean. So I'll plug in f of 1. That's gonna be 3 times 1 cubed minus 7 times 1 squared minus 22 times 1 plus 8. And if I plug that into my calculator, and I highly recommend if you're plugging this into your calculator, if you're doing it this method, then put all of the number that you're entering in parentheses. Because otherwise, when you have to plug in negative numbers, you'll have to add the parentheses anyways. 3 times parentheses 1 squared. And I know that 1 squared is 1. I get it. I know that's true, right? But because I'm going to be plugging this in for a bunch of different things, I'm going to put in parentheses. So 3 times 1 cubed minus 7 times 1 squared minus 22 times 1 plus 8. So people watching the recording, this is where you're going to be left out. But this is what I have in my calculator. Let me zoom in just a little bit more. So you can see. So I've put all of my zeros in parentheses and I press enter and it gives me negative 18. So write negative 18 in your notes. And then that's not 0. So x minus 1 is not a 0 of this polynomial. It's not a factor of this polynomial. Next, I'll try the negative version. I'll try negative 1. So if you have this type of a calculator, you can either press back, and that'll bring you back to what you just entered, or you can also press up. Up, not working on this one. Sometimes the calculator uses up to get into it. And then I'm just going to go to the beginning, and I'm just going to add on a negative sign each time. And then press enter, and I get 20. So on my notes, I'm switching back over for a second just so you can see it. F of negative 1, I get negative 20. So both times, this implies that x minus 1 and x plus 1 are not factors. So those didn't work, but that's okay. It didn't take us much work to do this. Sure, it took us a quick second to set up the first one, but now going back to my calculator, don't worry if you haven't finished writing that down, I'm coming right back to it. Or actually, I'll let you write it down. That's um hopefully written it down. Most people have. So then you can plug in 2. And so I'll show you how to do that. Don't worry if you haven't finished fully writing it down. I'm coming right back to it. But going back to this, now I'll just go back to it and I'll just delete all the negative ones and replace them with now 2. So I'm going to test 2. See if that works. Move it over. Just make sure that you've deleted all of your zeros. And I plug in 2 into all of it. And I get negative 40. So 2 doesn't work either. So write on your notes, f of 2 equals negative 40, and that also doesn't work. Then we'll try negative 2. So I'll go back into it, put a negative sign in front. Back in the day, this was tedious as all get out. But I plug in negative 2 and I get 0. So I'm going back to the notes now and see f of negative 2. F of negative 2 equals 0. And we get to put a green check mark. That means that x minus negative 2 is a factor. So we can use synthetic to break f down. recap that before we continue onwards once everyone's finished writing. And after this problem, we'll take a break. So once, oh wait, go ahead. Excellent question. So JT's asking, you only need one to equal zero. As soon as you know one of them equals zero, you can start breaking it down because now you know one of the factors. And so don't worry, I'm coming right back to this. But if you remember from last time, the factoring theorem, the big boy factoring theorem right here, if you know that f of c is equal to zero, which is what we just found out, then you know that f of x will equal x minus that c value times the quotient that you get from factoring it, from dividing by x minus c. So we can now use synthetic division to break it up into x plus 2 times something else. And you can find all of the zeros right now if you wanted to. We could go through, I guarantee you, if you sit down and you check them all, you will see that, what is it, negative 2/3, I think is one of the answers. Sorry, 1/3 and negative 4 will also work. So you can test them out now and find them all to get started with, or you can do it this other way, which we'll talk about in a second. But doing this now. So negative 2, oh, we didn't finish talking. So we found out that if we know that f of c is equal to 0, we know that x minus c is a factor, and then we can synthetically divide, or long division if you really want to break it down into pieces that can be factored further. So the rational zeros theorem tells us that if it does have a factor, it's one of these things. It's one of those zeros. So we'll start plugging them in until we find one of them that works. The rational zero doesn't tell you what the factors are. It tells you what the possible factors are. So we have to go through and test them out. And then we found that one. So now we'll synthetically divide. So f of x was 3x cubed minus 7x squared minus 22x plus 8. All factors of x are present, so we don't need to add any placeholders. And let's go ahead and do that synthetic division. I'll slowly fill in the details for you, but I'd like you to do it yourself. The bottom row, oh wait. And with some of those calculations, please feel free to use your calculator. If they start getting nasty numbers, go ahead. But bring down the first number, then multiply diagonally, and then add vertically. So negative 2 times 3 is negative 6. Negative 7 plus negative 6 is negative 13. Negative 2 times negative 13 is positive 26. Negative 22 plus 26 is positive 4. Negative 2 times 4 is negative 8. And they add together and they get 0, just like we'd expect. If we didn't get 0, that means that either we messed up here when we were plugging it in, maybe we forgot to delete a minus sign, or maybe we forgot to change one of the zeros when we were entering it into our calculator. Like, right, going back to this for just a quick second, like maybe when I'm changing it, maybe I did these three, but I missed this one and it was still a positive 2, right? This won't work. This will give me negative 88 because I forgot to put the extra negative sign right there. So there's two options when if you do the synthetic division and you don't get 0, either you made a mistake earlier on when you were plugging it into your calculator, or you did an arithmetic error down here. Check both, see what happens. But either way, we got this. So that means that f of x can be rewritten as x minus -2, so x plus 2 times 3x squared minus 13x plus 4. And remember, it's always going to be 1 degree less than your original thing. Whenever you divide by a degree 1 polynomial, your quotient will be 1 less degree. So our original function is degree 3. We divided by x to the first power plus 2. And so the quotient should be an x squared. It should be a quadratic. Any questions so far? The rational zeros theorem says that we can do it for any polynomial. So we could use RZT again. But let's just factor. Let's just factor by normal. It's quadratic. We know how to factor quadratics. And so this equals x plus 2. And then this will be 3x and an x. And they're both going to be minuses. And it should be 4 and 1. Yeah. Don't worry if you didn't get don't worry about getting to it that point that quickly. This takes time. Use AC box method or bottoms up method or anything that you've got at your disposal to factor it. But just in the interest of time, because I want to get us on our break. We've been going at it for over an hour, so it's time to get a breather. But that allowed us to factor it completely when we couldn't otherwise. Wow, such a useful skill. Thanks, Jesse. I know that's a super useful skill. I'm glad you recognized. So we're gonna take a break now. We'll come back at 10. Let's do 10:20. Let's take a 10-minute break. We've been going for a long time, and then we'll pick up again. Okay. Watch an recording, go do some guided meditation, or send an email to your representative. Back. So during the break, JT asked an excellent question of, could we have just continued going and plugging in all the possible zeros? Because, right, this will give you the 0 at 1/3. This will give you the 0 at 4. And if you look up above, 1/3 is a possible solution, a possible 0, and 4 is a possible solution. So you can find all of them right from the get-go. However, we run into a little bit of a snag that we also saw earlier on in this problem when we were doing this one. You can find all the zeros, but in order to break it down fully, you have to keep working on the next piece in order to factor it. So we had that one situation where I was going through this and I tried using 3 on the original polynomial again, but that just gives me another way to write the polynomial as a factor, as a product of a linear term and a cubic. But yes, you can find all the zeros right from the get-go.
I think more so like if you when we do the synthetic division result, where it's the -2, if you put the 4 then, are you going to come out with the same answer?
Yes and no. You will eventually get to the same answer. But actually, let's go ahead and do that. What happens if you decided not to go to 2 and -2? Let's say you just jumped around and you saw that you'd see that f of 4 is equal to 0. So then you'd use 4 in your synthetic division with 3x cubed, -7x squared, minus 22x, plus 8. And then you do the synthetic division, bring down the 3. 3 times 4 is 12. That gives me 5, which gives me 20, which gives me -2, which gives me -8, which gives me 0. So this would tell me that you could write it as x minus 4 times 3x squared plus 5x minus 2. So it's not the same factorization, but I can still get to the end result. I'll just have to factor that one instead. But that one factors, this one factors to 3x minus 1 and x plus 2. So we got all the right factors just in a different jumbled order. So it doesn't matter which one you start with, but in order to break it down further, you have to break up each next piece separately. And we'll see that in this next problem. So this one right here, factor the polynomial completely. We've got x to the fourth plus 4x cubed plus 3x squared minus 4x minus 4. So by RZT, possible zeros are x equals plus or minus. Let's write off Pucan Sam, right? A sub 0 over A sub n. Factors of A sub 0 over A sub n. That's why it's Pucan Sam. I'm going to write P sub 0 over Q sub n. And that'll be plus or minus. A sub 0 in this case is 4. Well, negative 4, but either way. So the factors of A sub n, sorry, factors of A sub 0 are 1, 2, and 4. And then there's an implied 1 here. So the factors of A sub n are 1. That's it. These are my favorite ones because then there's only, like, the denominator is only ever 1. So you only get integer numbers, which is really nice. Once you start dealing with fractions, it's never fun. But this will be, so plus or minus 1 over 1, which is just 1. Plus or minus 2 over 1, which is 2. And plus or minus 4 over 1, which is 4. So we have 6 things to check. All right. So now we'll just plug them into our into the function, see if we get 0, and move on from there. So P of, let's do 1. See if that works. So I'm writing it down in our notes, but on an exam, you could just plug it in your calculator, write down what the number is. Let's see here. 1 to the 4th power, and I'm putting that in parentheses because I'm going to be plugging in I'm going to be using this equation in my calculator multiple times because I know what 1 to the 4th is. It's just going to be 1, but I'm going to need to do this for other numbers too. Plus 4 times 1 cubed plus 3 times parentheses 1 squared minus 4 times parentheses 1. Is that a minus sign? Yeah, minus 4. You got error? Probably means that you forgot a parenthesis at some point, or put in too many parentheses, or forgot a symbol. So I plug in 1 and I get 0. So cool. My first guess worked out. So this means that P of so I can use synthetic division. So 1x to the 4th, 4x cubed, 3x squared, negative 4x, and negative 4. Good news is that all powers of x are present, so I don't need any placeholders, and I'll do the synthetic. So we get here, you should get in the bottom row, you should get 1, 5, 8, 4, 0, meaning that P of x can now be rewritten as x minus 1 times x cubed plus 5x squared plus 8x plus 4. I'm going to call this cubic. This one right here, I'm going to call this Q of X. For quotient. You know it because it is the quotient from doing the long division. Any questions so far? JT, were you able to figure out where the error was?
Yeah.
Okay. So from there, now we have to break it down further. I don't know how to factor cubics. I don't have the cubic formula memorized, so we're going to have to do the RZT again, but this time on Q of X. If we continue on with P of X, we're just going to keep finding new ways to write it as a linear term, like an X minus blank, and then a cubic term. So we want to break down Q, so we're going to now do the rational series theorem on Q of X. So now use RZT on Q of X to break down. So possible zeros of Q are going to be X equals plus or minus 1, 2, and 4 again. Just to save on time, hopefully you can see why take a second. It's like you can reuse the RZT on any polynomial. So in particular, we can use it on Q. Who can, Sam? Factors of a sub 0 over factors of a sub n. Factors of a sub 0 are 1, 2, and 4. Let me highlight it for the people watching the recording. The factors of a sub n or a sub 0 are 1, 2, and 4. The factors of a sub n here are 1. So it ends up being the same numbers, but that's kind of by design. It shouldn't have new zeros. All the zeros should have been present from the get-go, but either way. So now we'll plug those in. We'll do Q of 1. That's going to equal 1 cubed plus 5 times 1 squared plus 8 times 1 plus 4. And if I plug that into my calculator, plus 5 times 1 squared plus 8 times 1 plus 4, I get 18. And yes, I know I already checked 1 in P, right? I already checked that 1 worked in P and I found that 0. But that's not to say that 1 isn't a double factor, right? 1 could have a multiplicity of 2. It could have a multiplicity of 5. So we have to test it each time just to make sure. The good news is if we know that something isn't a 0, then it can't be a 0 of the next thing. I think we'll see that in the next one. But then we'll try, let's do Q of -1. Q of -1. So I'll just add a negative sign in front of all these parentheses, on the inside of these parentheses. And I get 0. So x plus 1, x minus -1, right? X minus -1, which is really x plus 1, is a factor of Q, which means that it's a factor of P, but we'll get there. So we can use synthetic division again, -1 into Q of x. 1x cubed plus 5x squared plus 8x plus 4. Bring down the 1. -1 times 1 is -1. Add vertically. That'll be 4. -1 times 4 is -4. That'll give me +4. -4 gives me 0. Because I plugged in -1 into Q and I got 0, that means that x plus -1 is a factor, which means that if I synthetically divide, I should get a remainder of 0, which I did. And so here's the little extra step. This means that Q of x is equal to x plus 1 times x squared plus 4x plus 4, which therefore means that P of X is equal to X minus 1 times X plus 1 times X squared plus 4X plus 4. Takes a long time to write, so I'll let you write that down and then we'll re-explain. And so this thing isn't fully factored down while you're writing it down. It's not fully factored yet. So we could use the RZT again, but no need to. It's a quadratic. We know how to factor quadratics. And I promise you on the exam, I will make sure that no matter how you start, how you finish, if you get down to the quadratic, you don't need to use the RCT again to do it. So, yes, GD.
Are you just adding the X minus 1 now because it's the original?
Yes, exactly right. So JT's asking, am I just adding the extra one? So doing this synthetic division, we did this on Q. So now we know how Q breaks up, but Q is this. So now we found a way to factor P down further. So this Q is now X plus 1 times X squared plus 4X plus 4. So P of X has that additional X minus 1, and then we have that. And then that factors further. That'll factor to P of X equals X minus 1 times X plus 1 times X plus 2 times X plus 2. Or you could write it as X minus 1 times X plus 1 times X plus 2 squared. I'm okay with either. Yes, Tori.
Jason, but do you have to find multiple zeros, or is it like once you find one, then you're done?
So once you find one, that'll help you break it down. And then you can use more to break it down further. So like you start with one of them to break down P in this case down into a linear term with a cubic, and then you'll work on the cubic to break that down. So it's kind of like imagine if you're trying to break down a Lego, right? You break down into big pieces and then you break down the smaller pieces as you go along. I guess not necessarily. I mean, some people break down their Legos in different ways, but it's this iterative process of breaking it down each step further and further. All right, next one. So this is y, but remember, y is synonymous with f of x. So you could write y of x if you wanted to. So let's see here. So this is a sub 0. Factors of a sub 0 are 1, 2, 5, 10, 25, and 50, right? Any other factors of 50? 150, of course, and then 50 divided by 2, that's 25, so that gives you the other one. 5 divided by 10 gets you the other one. Don't think there's anything else. Yeah. And then the factors of a sub n are 1 and 2. So I'd like you to list out the possible rational zeros. You can do it however you want. I usually do it by fixing the denominator factor and then listing all the possible numerator factors. Start this on the left-hand side because there's a lot of them. Who can Sam? P sub 0 over Q sub n. So 1 over 1, 2 over 1, 5 over 1, 10 over 1, 25 over 1, and 50 over 1. Which you never need to, like, if you're divided by 1, that doesn't do anything. So that's why I've just written 1, 2, 5, 10, 25, and 50. Then we move on to the next factor of a sub n as a denominator. So 1 over 2, that's 1/2. 2 over 2, that's 1. We already listed that. 5 over 2, that's new. 10 over 2, that's 5. We've already listed that. 25 over 2, that's new. 50 over 2, that's 25. We've already listed that. So those are our possible zeros. A lot of them this time. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's going to be 18 terms to test. But we have a calculator, which will make this much faster. So we'll start plugging them in. I'll do y of 1. 2 times 1 to the 4th minus 1 cubed minus 20 times 1 squared plus 5 times 1 plus 50. Let's see if that works. And pray. Times 1 squared plus 5 times 1 plus 50. I get 36. So that doesn't work. And once again, as a reminder, I'm plugging it in and I'm writing down all that notes for our notes so that we see what we're doing. We're plugging it into the function. But on an exam, on your homework, whatever, just plugging it in so that you know what you're doing is fine. I'll try y of -1. Hope that works. And if it doesn't, the good news is this doesn't take too long to plug into the calculator. I get 28. So that's not going to work either. I'll try 2. So I have to delete the -1 and put in a 2. I get 4. So that's not going to work either. Ugh. But let's try -2. Maybe that'll work. And lo and behold, it will. I didn't plug it in. I just know because I've got my notes in front of me. But it does work out. So that's good news. So we'll go ahead and synthetically divide. We know that x minus -2, which is x plus 2, we know that's a factor. So we'll set this up, the synthetic division. 2x to the 4th minus 1x cubed minus 20x squared, 5x, and 50. All powers of x are present. Good news for us. Bring it down to -4, -5, 10, -10, 20, 50, and 0. Good, good. It does work out. If we didn't get 0, that means that we made an error somewhere, either in the plugging into our calculator or in our synthetic division. Since we got 0, we know we're good. Right? So this means that y, or y of x, you can write it as y of x, it doesn't hurt. Y of x is equal to x plus 2, because it's going to be x minus -2. That's why it's x plus 2, times 2x cubed minus 5x squared minus 10x plus 25. Any questions so far? And I know this is tedious, but at the end of the day, it is marvelous because it gives us a way to factor when we couldn't before. Like, And yeah, it's not great. It's not efficient by any means, but it's the best that we can do. There's no formula anymore. There's no technique. This is the best technique that we've come up with. Maybe some mathematician later on will think of something. Maybe they'll prove a new theorem that allows us to find zeros very fast. But as it stands right now, there's nothing faster that I know of. Be really cool if someone figured that out, though. All right. So we get x plus 2 times 2x cubed minus 5x squared minus 10x plus 25. Now, you might be clever and notice that you can factor by grouping. There is a way to factor this by factoring by grouping, right? Splitting it right down the middle like we did before, way back when. You could do that, but who's to say that on an exam that you're being that clever and you're thinking about that right now? So let's just use RZT again. Let's call this Q of X. And do RZT on Q of X. So the possible zeros here are x equals plus or minus. Now we've got 25 and 2. So you can write it down if you'd like. I have a feeling we'll save the last one for next week. So I might have to extend the due date of 2.4 homework and 0.8 homework. But either way, factors of a sub 0 are 1, 5, and 25. Factors of a sub n are 1 and 2. So we've got 1, 5, and 25. And then 1/2, 5 halves, and 25th halves. Here's a fun little observation. I'm going to not even bother plugging in 1 or -1 because I know they won't work. Think about why. Why do I know that I don't even need to bother plugging in Q of 1 and Q of -1? Exactly right. If they don't work with the first one, they can't work with the second one because this is a part of Y. So if one worked in this, it would have worked in this, and it didn't. So we can skip it. Doesn't hurt. You can still plug it in, right? Your calculator is not going to get angry at you for plugging in 2 extra calculations. So it's chill, but just to save yourself some time, I'm going to save us some time right now and say that we can find out that Q of 5 halves equals 0. Oh no, it's a fraction. That's okay. We can have fractions. You can have a fraction. Let's do it. So we're setting it up. We know that x minus 5 halves is a factor of q. So we'll synthetically divide q by this, 5 halves, and we've got 2x to the third minus 5x squared minus 10x plus 25. All powers of x are present. That's good news. And so this does look intimidating at first, but it's just numbers. Feel free to use your calculator. So bring down the 2. 5 halves times 2, that's just 5. And -5 plus 5, that's 0. 5 halves times 0, that's 0. -10. And then 5 halves times -10, the half and the 10 cancel, you just get a 5, you get -25. But you can use a calculator. Please do so if you want. And so we now know that y of x, I'm going to skip that intermediate step I'll let you finish writing before I go on. And I know this takes up a lot of space. I wrote what Q is factored to in the first one, but now I'm just going to skip that step now that we know how to do this. So it's going to be x plus 2 times x minus 5 halves times 2x squared, right? Q of x is a cubic. We're dividing by a linear term, a degree 1 term, so our result should be a quadratic. 2x squared plus 0x, so I just won't write that, minus 10. And this right here, let's use pink. You could factor out a 2, we get x squared minus 5. And this is a difference of squares. What, Phil? 5's not a perfect square. So I'm going to put the squares in quotation marks. Remember, I think we had this conversation when we were talking about factoring. Anything can be a difference of squares if you want it bad enough, right? We can just write 5 as square root 5 squared. So this thing actually does factor to finally y of x is equal to x plus 2 times x minus 5 halves times 2 times x plus the square root of 5 times x minus square root 5. And that is our answer. We can put the 2 out front if we really want to. If we really want to. But unnecessary. It's good enough. Alex will accept it. I'm sorry to keep you 1 minute late. That'll do it for this week. The last question is an extension question, so it's not actually going to be a question on your homework. So you don't need to worry about that. You have everything you need for 2.4. 2.4 is very, very quick. There's only like 4 topics on there. Wesley. Say what? The 2x squared minus 10. You see it? Okay. So I'm not going to extend the due date of unit 2.4 because this is like the next problem is just a bonus problem. It's an extension problem. You have everything you need to know for 2.4. If you guys have any questions, feel free to email me. Otherwise, you guys have a great rest of your day, a great weekend. Spend time with the people around you. Social media isn't real. You know the deal. Limit your social media exposure and have a great weekend. Avoid the endless scroll and write to your Congress people.